Imagine standing in the middle of a completely empty field. In a few years, you must turn this dirt into a massive, humming industrial complex. In engineering, an empty field is a greenfield project, a blank slate. Contrast that with a brownfield project, expanding an already operating factory. Greenfield gives total design freedom, but starting from zero means the initial capital investment is enormous and financial risk is high. When you have an open space, it is easy to make assumptions, but a minor miscalculation early on, say putting a concrete foundation 3 feet in the wrong direction, will force engineers to completely redesign highly expensive systems months later. To prevent those expensive mistakes, engineers follow a strict order of operations. They build the plant the exact same way nature develops a biological body, one system at a time, each depending entirely on the one before it. Building this system is a relay race. Process engineers define the chemistry, mechanical teams design tanks, and instrumentation maps sensors. Then we reach the most intensive step, piping. These arteries must be routed before civil pours concrete and electrical runs power. Of all these complex systems, that piping network dictates the financial success of the entire operation. These two charts compare the required engineering effort against final construction costs. Designing the piping consumes roughly 40% of all engineering hours. When it is time to build, buying and installing those specific pipes accounts for 30% of the entire facility's price tag. Because piping takes up such a massive portion of the budget, keeping a tight grip on this specific discipline is the single most effective way management can protect the project's profit margins. To keep piping costs controlled, engineers rely on 2 maps. The first is the Process Flow Diagram, or PFD. Think of it as a recipe. It tracks materials, temperatures, and equipment to prove the chemistry works, but lacks physical details needed for construction. That is where the master blueprint comes in, the piping and instrumentation diagram. The P&ID plots the location of every pipe, valve, and safety lock. This blueprint is legally binding. If an item is not drawn on the P&ID, it will not be built. Engineers take this flat blueprint and build a complete virtual 3D replica of the plant. This digital twin lets them check that no pipes crash into each other, and it generates an exact shopping list of thousands of parts for the purchasing department. We track the timing and cost of this 3D modeling work on these 2 graphs. The Gantt chart on the left maps out the strict timeline, while the S-curve on the right tracks the cash flow. Monitoring these lets managers spot bottlenecks before they drain capital reserves. Once the planning is finished and the facility is turned on, the environment changes entirely. Those static pipes become dynamic, moving entities, forced to handle intense internal pressure and boiling liquids. To survive those forces, engineers perform stress analysis. They calculate how the metal stretches when heated and vibrates as chemicals rush through. If they skip this math, mechanical stress will rip the steel anchors out, tearing equipment apart and releasing lethal chemicals. To prevent failures, teams must pick exact materials. This matrix shows how utility systems require different metals. A cheap material for high-pressure cooling water causes blowouts, while expensive alloys for basic service water destroy budgets. Engineering balances safety and finances. Because the physical risks are severe, engineers operate under massive, heavily enforced industry rulebooks, such as the ASME codes. These dictate exactly how different systems must be designed and built. Following these design codes is a strict legal requirement. They act as a corporate shield, ensuring that the final facility protects the workers on site and the surrounding communities from industrial accidents. Succeeding in a greenfield build requires strict discipline. First, freeze P&ID blueprints early to prevent expensive redesigns. Second, carefully manage the massive capital tied to piping. Mandating safety standards and controlling engineering flow transforms empty fields into profitable industrial realities.